I want you to help me solve this problem. Look at the circuit here. We have a voltage source that varies between 15 volts to 24 volts. Now we have a sensitive instrument connected to this voltage source, but there is a condition. We need to maintain a constant voltage of 7.5 volts across this instrument. So now what we need is a regulated or a constant voltage, and what we have over here is a varying or an unregulated voltage. Now how can I obtain a constant or regulated voltage from this unregulated voltage? Now we are given a Zener diode. This is the circuit symbol of a Zener diode. So we are given a Zener diode, and the breakdown voltage of this Zener diode is 7.5 volts. So that's great. This should help us solve our problem, which means, so if I connect the Zener diode here, then the voltage across this Zener diode stays at 7.5 volts. So the voltage across the sensitive instrument that I have connected over here will also remain at 7.5 volts. Now are you wondering what breakdown voltage means? Okay, so then let's quickly recall this from the reverse characteristics of a Zener diode. I'll just draw them here. This is the voltage and this is the current, and this is the constant voltage, the voltage that doesn't change, and over here for this particular example it has a value of 7.5 volts. You can see that this is the constant voltage across the Zener that does not change even if the current through the Zener varies over a fairly wide range, say from about this value to this over here. Now see on the graph I have marked two values of the current between which the Zener is operated. This is the range. This value over here is called the knee current. This is the minimum current which needs to flow through the Zener, and this is the maximum current which flows through the Zener. See, the current is less than the knee current. This is called the knee because this looks just like a knee over here. And if the current is less than this, then the resistance of the diode is very large. And you can also see this from the VI graph, because the reciprocal of the slope of this graph, which means dV over di, will give you the resistance, and since the resistance is very large, the current is almost zero. And when the current is almost zero, then the diode is off. The diode is not conducting any current. So if the diode is not conducting any current, which means the diode is off. See, if the diode is off, this means that the voltage across this sensitive instrument that you have connected over here, or it could be any load, will also vary in accordance with the supply voltage. But what we want is a constant voltage across this instrument. Now again, coming back to this graph, we also have a maximum value of current that can flow through the diode, and this is found from the power rating of the diode. The power is equal to V times I. So let's say we have a diode whose voltage is 7.5 volts and it has a power of, let's say we have a diode whose breakdown voltage is 7.5 volts and whose power is 1 watt. In that case, the maximum current which can flow through this diode is 1 over 7.5, and that will be in amperes, and if I write it in milliamperes, this will work out to be 133 milliamperes. So the maximum current which can flow through this particular diode would be 133 milliamperes, and generally the knee current is mentioned in the specifications of the diode. For instance, I could have this diode which has a knee current of about 0.5 milliampere. Now I'm sure you must be thinking that what happens if you exceed the current. Now we are saying that there's a limitation, but what will happen if you exceed the current? Now if you exceed the current, then the Zener will become very hot, and if the Zener becomes hot, it can simply burn out. So one would normally operate the Zener within this range. If the current is maintained between this minimum value, which is the knee current, and the maximum value, then we get a constant voltage Vz, which is, say in this particular case, 7.5 volts across the load. Now apart from placing the Zener in the circuit, we also need to place a series resistance over here, and we will denote this by Rs. Now I'm going to calculate the value of Rs for some particular values of the supply voltage Vs and the load resistance value, which is equal to 300 ohms. Now say we are given that the breakdown voltage of the Zener is 7.5 volts, the knee current is 0.5 milliampere, the maximum current is 121 milliampere. If you recall, we found the value as 133 milliampere, but this is according to the sheet, the specifications given for the diode. So that will be less than the maximum possible current, so which is 121 milliampere. The source voltage is given as 20 volts. The load resistance is 300 ohms, and we need to find the value of the series resistance. We are given that the current through the Zener is 1/4 of its maximum value, which is about 1/4 of the maximum value, which would be about 30 milliampere. See, we are given this value of current because for this current the Zener is most stable and the voltage remains more or less constant, because we are operating in the linear part of the graph. So it will give us the best output. So it is given that the Zener current is 30 milliampere, and now we need to find the value of the series resistance. You can see from the circuit over here that the series current Is is equal to Vs minus Vz over Rs. So we can write this as Vs minus Vz over Rs. The load current in this part of the circuit through the load resistance IL will be given by Vz, the voltage across the resistance, which is the same as Vz. So IL is equal to Vz over RL, and you can see that the current over here, which we'll denote as Is, is the sum of the current through the Zener and the load current. So say we denote this by Iz. So Is is equal to Iz plus IL. Now using these equations you can find the value of Rs, and IL comes out to be 7.5 over 300, which is about 25 milliampere. Iz was 30 milliampere, so Iz plus IL is Is. So Is is 30 plus 25, which is 55 milliampere. Now we can find Rs, which is Vs minus Vz over Is, and if you calculate this comes out to be, see, this will be 20 minus 7.5 over 55, and this comes out to be close to 220 ohms. We get a value which is 27 ohms. So now you can use a standard resistance of 220 ohms, because a slight variation in the resistance won't make much of a difference, because the current through the Zener will change, but the voltage across the load will remain the same. So far, when we've talked about the Zener diode, we've said that the source voltage can vary, but it is also possible for the load resistance to vary. So even in that case, we get a constant voltage across the Zener as long as we are operating within the range from I need to I max current. Suppose RL changes to, let's say, 500 ohms. In that case, the load current will change to 7.5 over 500, which is equal to 15 milliampere. Now, the source current over here is 20 minus 7.5 over, and we found a value of 220, and this was about 55 milliampere. And you have a current of 55 minus 15, which is 40 milliampere, will flow through the Zener diode. See, the advantage of a Zener diode is even if the current through the Zener changes, the voltage remains fixed. So over here now the current has changed to 40 milliampere. You have a greater current flowing through the Zener diode, but the voltage across it remains the same at 7.5. So the voltage across the Zener can remain the same whether the source voltage changes or the load resistance changes. Thank you.